We think we're living in astronomy's golden age. Hubble changed how we see the universe. Webb showed us things we were never meant to see at all. And yet, astronomers are saying something strange. We're still looking through a keyhole. Not because the universe is hiding, but because our mirrors are still too small. Planets with atmospheres vanish in their star's glare. The first stars whisper from the edge of time. Dark matter bends light, but never quite enough. The problem isn't imagination, it's photons. And that's about to change.
You've seen Hubble and Webb. So why are astronomers saying we're still peeking through a keyhole? Today we're stepping into the era of megatelescopes, where a leap in light-collecting power changes what we can actually know.
When I first started working with this project, I met with someone who had been working on it since 1996. We want to go really deep and observe things that are from really far away, which essentially means in astronomy that they're from earlier times.
In the next few minutes, you'll see how bigger mirrors unlock exoplanet atmospheres, why first-generation stars have stayed invisible, and how dark matter's web will finally be traced. Stay with me, because the difference between nice images and new physics comes down to one thing: area. If Webb stuns us, why do biosignatures still vanish inside starlight that's 1,000,000 times brighter than the planets that carry them? The keyhole problem is simple. Telescopes can show striking images, but the faint signals we care about ride on top of a glare that refuses to go away.
So it's really humbling on one side, but also it makes you realize that this is like an endeavor of a generation of astronomers.
Exoplanet atmospheres leak a tiny fraction of light during a transit. The first stars sit so far and so redshifted that their fingerprints get smeared into the background. Dark matter only reveals itself indirectly, distorting galaxy shapes by a small amount. These are whisper-level signals. We've had great cameras. What we lack is enough light to turn those whispers into sentences. 3 bottlenecks set the ceiling. First is light collection. Too few photons and noise wins. Second is angular resolution. You need a fine point spread function to separate a planet from its star or to sharpen a lensed galaxy's edges. Third is stability. Spectroscopy at extreme contrast calls for wavefronts that barely drift, or else speckles masquerade as features. With mirrors like 2.4 meters and 6.5 meters, you hit hard limits when you ask for deep, high-contrast spectra rather than pretty scenes.
If you took your finger and held it at arm's reach and put it up to the sky, potentially, depending on where you're looking at, tens of thousands of galaxies will fit into that one little portion of the sky that is covered by your finger.
Think about trying to count fireflies next to a stadium floodlight. With a small mirror, photon noise from the star dominates your detector. Speckle noise, born from tiny optical imperfections, scatters starlight into a mottled pattern that looks suspiciously like a signal. The smaller the mirror, the brighter that false texture is compared with the planet. You can stack exposures, but the noise shrinks slowly and the clock beats you. Light gathered grows with area. Scale a 6.5 meter up to a 39 meter, and you multiply the collecting area by roughly 36. That moves you across the line where faint spectral lines flip from tentative bumps to clear detections. Exposure times shift, too. What demands many transits with a smaller mirror can compress into fewer nights, or the same time can buy far higher spectral resolution, letting you resolve narrow molecular lines and measure motion. On the ground, adaptive optics makes the atmosphere behave.
So what we have here is a colorized pair of merging galaxies. My laptop screen hardly does it justice, but I hope that gives you a sense of scale of what we're looking at, even nightly.
And now imagine that over the entire southern sky, we're getting an unprecedented data set, not just of galaxies, but of variable stars and near-Earth objects as well.
By sensing distortions hundreds to thousands of times per second and reshaping mirrors in real time, AO sharpens the image to the diffraction limit and cuts speckle noise. Extreme AO takes that stability further and feeds coronagraphs that suppress starlight while keeping the planet. All of this sets up the next step. Segmented giants tuned for exoplanets and early universe light are coming, and their photon budgets change the questions we can ask. So which machines are built to cash in on that area, and what new signals move within reach? What happens when a telescope's mirror is the size of a house and its optics can freeze Earth's turbulence in real time? Meet the new heavyweights. On the ground, 3 giants lead the charge. ESO's extremely large telescope in Chile, the giant Magellan Telescope not far away, and the 30-meter telescope planned for the Northern Hemisphere. In space, partners focus on stability and wide, quiet fields. The idea is simple. Let the ground deliver raw photon power and fine detail, while space platforms provide the calm, drift-free baselines that precision work needs. The question is whether these machines can actually pull out biosignatures, spot the first generation of stars, and map dark matter threads, or if they are just scaled-up mirrors. Their designs say they reach further. The LT pushes a 39-meter primary with about 978 square meters of collecting area. Its 5-mirror optical train includes a deformable mirror that reshapes at kilohertz rates, flattening wavefronts before they smear the image. Its instrument suite spans the key bands and modes. METIS for mid-infrared thermal light, Harmony for integral field spectroscopy that captures spectra for each pixel at once, and HIRES for high-resolution spectroscopy that isolates razor-thin lines. Here's the math that matters. The jump from a 6.5 meter to a 39 meter is not a factor of 15 in diameter. The sensitivity boost follows area. The ratio goes roughly as 39 divided by 6.5 squared, about 36. GMT uses 7 8.4 meter segments working as one, giving around 368 square meters. TMT's segmented 30 meter hits roughly 655 square meters. These numbers lower noise floors and push detection limits down to signals we could not separate before. Ground and space split the workload by physics. Space offers ultra-stable point spread functions and no atmosphere, ideal for long, steady sequences and wide surveys. The ground wins on aperture, extreme adaptive optics, and the ability to upgrade instruments and algorithms. Coronagraphs suppress starlight. Nulling interferometry cancels it by phase tricks. When HIRES-class spectrographs reach resolving power above 100,000, they start to see the comb of individual molecular lines in an exoplanet spectrum. Because a planet orbits, those lines shift in velocity, sliding against the star's spectrum and letting software lock onto the planet's fingerprint. All of this points toward 3 targets waiting just ahead: Earth-level atmospheres nearby, the first stellar populations, and the faint shear of the cosmic web. The specs unlock high contrast, high-resolution spectroscopy, and deep, AO-sharpened imaging that were out of reach. So the next question is how soon each frontier will yield its first clean signal, and which facility gets there first. Which lands first? A breath of life in a nearby atmosphere, the first unmistakable mark of a population 3-star, or a crisp map of the universe's hidden skeleton. Start with the atmospheres. Pulling out O2, O3, CH4, and CO2 from an Earth-sized world means scraping signal out from under a star that drowns everything. The hurdle is contrast. A rocky planet reflects or transmits a tiny fraction of light. We're talking planet-to-star ratios from 1 in 10 million down to 1 in 10 billion. Gas giants are easy by comparison. Rocky worlds demand sharper optics, more photons, and a way to separate the planet's moving signature from the star's fixed glow. That's where high-dispersion spectroscopy joins adaptive optics and coronagraphy. AO steadies the wave front, coronagraphs blunt the star, and a spectrograph at resolving power around 100,000 breaks light into thousands of narrow channels. Then you cross-correlate the data with molecular templates. Because the planet orbits, its lines slide in wavelength across the night. The star's lines stay mostly put. Stack nights, track that Doppler shift, and the planet's pattern rises. Simulations point to oxygen at the 0.76 micron band around temperate M dwarfs with ELT-class area and multi-night campaigns, while GMT and TMT extend sensitivity in the near-infrared for water, methane, and carbon dioxide. Now the first stars. Population 3 stars form metal-free, burn hot, and die fast. By the time their light reaches us, expansion has stretched it deep into the infrared, and any signal is blended into faint host galaxies. The tactic is to use gravity as a telescope. Aim at strong lensing fields where galaxy clusters boost background light by factors of 10 to 100. Then push deep spectroscopy on the magnified arcs, hunting for metal-poor clues like strong helium-2 at 1640 angstroms and a lack of heavy element lines. Echoes from parent stability supernovae, broad features, and unusual ratios offer an independent flag. JWST identifies the highest redshift candidates. The ground giants provide the photon counts to split their spectra and test for primordial chemistry. Finally, dark matter's web. We see galaxies, but the mass we need is in the filaments between them. Current weak lensing maps blur at large scales, raise the density of galaxy shapes, and add precise redshifts, and tomographic reconstruction sharpen. YLT and GMT class surveys supply deep shape catalogs and spectroscopic distances. Euclid, Roman, and JWST deliver stable, wide fields. Together, they lift resolution and time the discoveries through the 2030s, each platform locking in what the other reveals. The next era isn't about prettier photos. It's about gathering enough photons to swap guesses for measurements, and stitching a single map that runs from nearby biosignatures to the universe's first light. That's the shift, turning faint hints into testable numbers. Keep an eye on first light milestones and build-outs. YLT, GMT, TMT on the ground, with Euclid and Roman in space, because discovery windows open fast and stay narrow. Instruments roll in, targets align, and then they move on. When area meets stability, the keyhole becomes a doorway. The 2030s will show what's alive, what came first, and the hidden framework holding it all together.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.